Good morning. Hope you don't mind having a videotaped lecture for a couple lectures this week. First of all, please remember, if you have not signed one of the attendance sheets for the no-show policy for this class, 1112 lecture, please make sure to go see Mr. Fred Bulls in room CC 1190 and ask him if you can sign one of the attendance sheets for my Jim Gwynn 1112 lecture class. Please make sure to do that. It is imperative that you sign at least one attendance sheet so that you do not get no-showed for the course. Okay, last time we were talking about the electrostatic force, the force between two charged objects. We are going to continue with that today and start looking at some different aspects about that force. There's actually a problem with this force. It's a similar problem as with the gravitational force, and this is a problem that Isaac Newton recognized and wasn't actually able to figure out a solution to it, wasn't able to understand how to get around this problem, but we'll actually figure out a solution to it. First, let's imagine we have two charged objects. So maybe we've got two charged spheres here, just making sure I'm in your field of view. So let's imagine we've got two charges here. They could be both positive, both negative, it doesn't really matter, just let's assume that they're both charged. We know that there is a force that exerts between them. If they are similar charges, say both positive charges, the forces are repulsive. If they're both negative, similar charges, again, forces are repulsive. If, say, one is positive and one is negative, there is an attractive force between them. Now, this type of force is a little bit hard to understand. If we actually have a contact between two things, maybe I push on this sphere, we can see where that force comes from. My hand exerts a force on the sphere and I push it. That's what we call a contact force. When there is a force between two objects that are not actually touching each other, this is called an action at a distance force. So this is a type of force that acts between two objects that do not touch each other. And obviously this is likewise the kind of force that we have between two objects that are gravitationally attracted to each other. The Earth attracts this pen. When I let it go, it falls down. The Earth pulls it down with a gravitational attraction. The Earth is not touching this pen. Somehow there is a force between them, even though there is a distance between them. It's not a contact force. Okay, so how do we understand this? We've got a little problem with this type of force. Now, let's look at it this way. We know that we can measure the strength of the force between these two objects. We talked about that last time. The strength of the force we can write as the magnitude is equal to Coulomb's constant, K, times the charge on one object times the charge on the other object. To be more specific, the magnitude of the charges. The signs of the charges actually come into the direction of the force. Similar charges repel, opposite charges attract, then divided by the distance between them squared. So we've got these two charges, let's say Q1, Q2. There is a distance between them, and to be a little more precise, we mean distance center to center, so to speak, a distance r. Be careful, this r does not stand for radius. This is just the position, vector, magnitude, the distance between them. So we've got k, q1, q2 over r squared. We know that there's a force between them with this magnitude. Now, what happens if we change the distance between the two charges? So let's imagine we've got these two charges here, and we move one of the charges closer to the other charge. What happens? Well, we've decreased r. We have a smaller r means larger force. The force between them increases. So as soon as I move this in, r is smaller, the force increases. Now the problem is, what if these two charges are actually very, very far apart? Miles, millions of miles, billions of miles, light years apart. Well, as soon as one moves, the force between them increases, according to this result. There is no delay or anything like that. The change in the force is instantaneous. As soon as r changes, the force changes. Now there's the problem. We've got this instantaneous, immediate change in the force when the distance changes. This would be a similar problem with the gravitational force. If you've got two objects with a gravitational attraction, as soon as you move one object, the force changes. Now, Isaac Newton even realized there's some conceptual difficulty with this. Things, millions and billions and trillions of miles apart, you move one, somehow the other one feels a change in that force instantaneously. So how do we get around this? Well, Michael Faraday came up with a way of explaining this. And he lived from 1791 until 1867. Now, I put these dates down not because I expect you to remember all of these dates, but just so we can kind of put this into perspective with perhaps other things that are going on in history at the same time. We know, well, let's see, 1791, that's somewhat after 1776, so he was born, sometime after the American Revolutionary War, just to give you an idea of when these sorts of things were taking place. Okay. What Faraday's idea was to imagine, let's start out with just one charge. Let's forget about the second charge for a minute. Let's just imagine one charge. This single charge, let's say with some magnitude q, creates something around it. Okay? We won't say what this thing is yet, what it looks like. We'll get to that in a minute. But it creates something around it. We'll call it a field. It creates a field around it. The field emanates from the charge, you might say, almost like a three-dimensional faucet. You have a faucet with water coming out of it into a sink. That water hits the sink and spreads out. Imagine this is some kind of three-dimensional faucet where it's creating this field and the field is spreading out into space in 3 dimensions. Now this field is what's going to create the electric force, so to be specific, we'll call this the electric field. So the charge creates the electric field. When we put another charge in the presence of this field, that charge experiences the field as a force. So imagine we've got another charge, so here's a small charge. We put this charge in the field of this force. This charge experiences that field as either an attractive force or a repulsive force. So if let's just say for the time being that Q is a positive charge, and we bring another positive charge in the field of this charge. This positive charge experiences that field as a repulsive force. It experiences the field by being pushed away from that charge. If this were a negative charge, this charge would experience that field as an attractive force. It would be pulled toward that charge. Likewise, if this were a negative charge, those forces would be reversed. This charge experiences the field that would be created by this charge. So this charge creates its field, this charge creates its own field, this charge experiences this, the field of this charge as its own force, etc., etc. So whatever, it's kind of symmetric. So this creates its own field, this one creates its field, and the two charges experience the opposite charge's field as a force. Okay. Now, how does that help us with this action at a distance? Well, first of all, it gives us a way to understand what is actually creating the force. It's the interaction, say the force on this charge is the interaction with this charge and this charge's field. So this charge actually has a field that exists over here, and the interaction between this charge and the field is what creates the force. Now, how does this help us understand this thing of how do these changes occur if they're miles and miles apart? Well, let's think about that. So let's imagine we've got these two charges here. This charge creates a field That field completely surrounds this charge throughout space. We put this charge in the presence of the field from this charge. This experiences that field as a force. Likewise, this charge creates a field. We put this charge in the field of this charge, and this one experiences a force. Now, what if we were to move one of these charges? Well, let's say we move this charge in closer. We've changed the location of this charge within the field of that charge. So by moving it, we change the interaction between this charge and the field, and so the force changes. So that kind of makes sense. If you walk on a hillside, you walk to a steeper place, you immediately feel that change, so to speak. Now, what about the change in the force on this charge? Now, this is where it gets a little more interesting and a little more difficult to understand. So we move this charge. How does the field from this charge change over here? Remember, the force on this charge is due to the interaction of this charge and the field created by this charge. So when we move this one, what happens to the force on this one? Well, the change in the field from this charge has to propagate through space to get over here. Almost like, imagine we've got some water and we've got two corks floating in the water. I move this cork up and down. Does this cork realize that this cork is moving up and down immediately? No, not immediately. I move this cork up and down. It creates waves that propagate through the water and finally come over to this cork. So this cork does not realize that this cork is moving up and down until the waves in the water propagate through all the way over here. It's a very similar sort of thing. We've got these two charges. I move this one over here. This one does not experience an increase in the force until the increase in the field has propagated through space to get over to this charge. So the change in the force is not instantaneous. It takes an amount of time for the change in the field to get from this charge over to that charge. So it is not instantaneous. So this makes a very good explanation to solve this action at a distance, instantaneous change in the field, instantaneous change in the force problem. By putting the field in between the charges, we have kind of this intermediary between the two charges to help understand what's going on and what's creating this force. So that's great. That's a great explanation. However, it leads to one more problem. If we'll remember, let's think about this again for a second. So what I said was we move this one in. This experiences a change in force instantaneously because we've moved it to a different point in the field of this charge. However, the force on this charge does not change until the change in the field has propagated through space. So, when I move this in, this charge feels a different force than this charge does during that time that we're waiting for the propagation through the field. Well, that means that object 1 creates a different force on object 2 than object 2 creates on object 1. Well, what's the problem with that? That's a violation of Newton's third law. If you remember, Newton's third law said that object 1, if object 1 creates a force on object 2 creates an equal and opposite force on object 1. To write it simplistically, or simply, the force F12, the force on object 1 due to object 2, is the negative of F21, the force on object 2 due to object 1. So Newton's third law basically states this: what we have just done by using this electric field is to violate Newton's third law. So what's wrong with violating Newton's third law? Well, it was from Newton's third law that we actually derived the conservation of momentum. If we violate Newton's third law, have we just violated the conservation of momentum? Well, that is a serious problem because there is a lot of stuff that depends on the conservation of momentum. How can we get around that? Well, it's a very, very interesting result. We derived the conservation of momentum from Newton's third law. So you might think, well, Newton's third law is a more fundamental idea. the conservation of momentum comes from that. Actually, it's exactly the opposite. The conservation of momentum is actually a more fundamental idea, and Newton's third law comes from that, from the conservation of momentum under certain circumstances. So it turns out the momentum really is conserved, and Newton's third law only works sometimes. And this is one of the cases where it doesn't work. Now, how can we conserve momentum in this case? We move this charge in, and imagine we've got this charge stationary here, a long way away. I kind of toss this charge in, it experiences the force, slows down, and stops, and then accelerates backwards. Where is that momentum that this charge had? This charge hasn't started speeding up and moving away, so where's that extra momentum? Well, it turns out that there is actually momentum carried in the oscillation of the field that's going from one charge to the other. So we still have a conservation of momentum. That extra momentum is carried along in the field as it propagates from the first charge to the second charge. So, a very, very interesting result. We still have conservation of momentum. The momentum is carried along in this oscillation of the field. However, we have violated, for a little while, Newton's third law while this momentum is carried along until it gets to the other charge, and then we can kind of get Newton's third law back. So, what are the properties of this electric field, assuming that this seems to work, which it does? What are the properties of the electric field? What does it look like? Well, to figure out the electric field, we'll actually look at the force exerted by a charge on another charge, and by determining the properties of the force, we'll try and figure out what the properties of the electric field are. So, let's imagine we've got some charge. So here's some charge sitting in space. We're going to take a very, very small charge, what we'll call a test charge. Now, we want this to be a test charge because we want to test what the field of this charge looks like without changing that field very much. So we'll assume we've got some big charge here, and then we're going to test the properties of the field created by that test charge. Test the properties of the field created by the large charge by using a little tiny charge. You might think of this as, excuse me, a single proton or something like that. Some very, very small positive charge. So we're going to bring this charge in, we're going to move it around this charge, this one, we're going to move it around and test what the field looks like. Well, first of all, we realize that the closer we get to this charge, the greater the force acting on the test charge. The farther away we get, the weaker the force acting on the test charge, because we know that the force acting on the test charge is going to be K times the magnitude of this charge times the magnitude of the test charge, and I'll use a little q for the magnitude of the test charge, over the distance squared. So the larger r, the smaller the force. We're going to use that idea to say, well, if the force is larger here and the force is smaller here, we're going to say then, well, maybe that's because the field is larger here and the field is smaller here. So the closer we get to the charge big Q, the stronger its field, the farther away, the weaker its field. Now, for the time being, let's just assume these are both positive charges. We know that close to this charge, the field points away like that. Over here, the field points away like that. So we'll say that the direction of the force, excuse me, the direction of the force is the same as the direction of the field if we have a positive test charge. So we'll assume we have a positive test charge. The direction of the force created by a positive charge here is away from it because we've got two positive charges. So we'll say that the electric field points away from a positive charge. If we have a negative charge and we put a positive test charge there, it's going to be attracted And so we'll say that the electric field points toward negative charges. So this is a very, very important point. Positive charges create electric fields that point away from them. Negative charges create electric fields that point toward them. So electric fields go away from positive charges toward negative charges as a general statement. And we'll come back to that. So what does this field look like? Well, we'll say that, again, let's assume we've got a positive charge. Close to the positive charge, we have a very strong field that points away. If we move further away, the field gets weaker. Further away, it's even weaker still. Always pointing away, and these arrows are supposed to point away from the charge here. Alright, so this is one way that we might represent the electric field. It's a little bit awkward with all of these different arrows all over the place, so we're going to simplify this a bit. We're going to draw it like this. So, here's our positive charge. We're just going to draw arrows like this. The directions of these arrows show us the direction of the electric field. So they show us the direction of the electric field, always away from the charge in the middle. But how can we show that it's stronger close to the charge, weaker further away? Well, notice that the lines that I have drawn are closer together, close to the field, and farther apart, close to each other, close to the charge, and they're farther apart from each other when you're farther from the charge. And so we'll use the density of lines, you might say, to indicate the strength of the field. When the lines are very close together, this means we've got a strong field. When the lines are far apart, this means we have a weak or weaker field, at least weaker than this point here. So we'll use the distance between the lines as an idea of the strength of the field. The closer they are, the stronger the field. The farther away they are, the weaker the field. All right, there we go. So there is a look at what the electric field looks like for a positive charge. For a negative charge, we would get something very similar. However, in this case, all of our lines point toward the charge, like that. So that's what the electric field would look like for a negative charge. Positive charges, the field lines point away. Negative charges, the field lines point toward the charge.